Somewhere in our galaxy, there may be an ocean with no shoreline, no beach, no coast, perhaps not even a clear boundary between the sky above and the water below. On one distant world, scientists have proposed a circular sea stretching roughly 4,000 kilometers, which is about 2,500 miles, locked forever beneath a sun that never rises and never sets. Another planet may hide a layer of water nearly 1,900 kilometers, which is about 1,200 miles deep. Earth's oceans, by comparison, average less than 5 kilometers, about 3 miles in depth. Elsewhere, astronomers have found worlds so close to their stars that any ocean would not be made of water at all, but of molten rock flowing beneath an atmosphere hotter than a blast furnace. Others may have begun with enormous oceans, only to watch them slowly disappear as relentless starlight tore their water apart, molecule by molecule, over billions of years. The strangest part is that no one has ever seen any of them. Astronomers cannot photograph their waves. They cannot map their coastlines. In many cases, they cannot even prove that a shoreline exists. Instead, they search for oceans indirectly, reading tiny changes in a planet's mass, atmosphere, temperature, and gravity, piecing together evidence across distances so vast that even light needs decades, centuries, or longer to reach us. How deep can an ocean become before water transforms into something entirely different? Can a planet contain so much water that it becomes less suitable for life rather than more? And how can an ocean survive beneath crushing pressures, endless darkness, or a sun that never moves across the sky? Quick favor before we continue. If you find yourself coming back to videos like these, hit subscribe so you don't miss the next one. It makes a bigger difference than you might think. The story begins with how astronomers can detect an ocean they may never actually see. Before we can imagine oceans hidden beneath distant skies, we first need a way to recognize a world we cannot truly see. An exoplanet is simply a planet orbiting a star beyond our own solar system. Across those immense distances, the planet itself usually disappears into its star's overwhelming light, yet its presence still leaves delicate fingerprints that patient instruments can measure. One of the most successful approaches is called the transit method. As an exoplanet passes across the face of its star, a tiny fraction of the starlight briefly fades. The change is extremely small, yet it can be measured with remarkable precision. A deeper dip usually means a larger planet because it blocks more light. From that repeating shadow, astronomers calculate the planet's radius and begin assembling the first pieces of an otherwise hidden world. Another technique listens for motion instead of shadow. Every planet pulls on its parent star through gravity, causing the star to sway ever so slightly. That motion changes the star's light in predictable ways as it moves toward us and then away again. Measuring those shifts allows astronomers to estimate the planet's mass, even though the planet itself remains beyond direct view. When mass and radius are combined, they reveal average density. This single value carries surprising weight. A very dense planet is more likely to contain abundant rock and metal. A lower density may point toward large amounts of water, ice, gas, or a combination of several materials. Even so, density rarely tells one complete story. Different interiors can produce remarkably similar measurements, leaving several scientifically reasonable possibilities. The atmosphere offers another source of evidence. During a transit, a small portion of starlight passes through the planet's upper atmosphere before reaching our telescopes. Certain molecules absorb specific wavelengths of that light, creating a distinctive pattern, much like a chemical barcode. This process, known as transmission spectroscopy, lets researchers identify atmospheric ingredients, without ever touching the planet itself. Additional clues arrive when the planet slips behind its star. Astronomers compare the combined light before and after that brief eclipse. The difference reveals heat coming directly from the planet. They also examine phase curves, gradual changes in brightness throughout an orbit that show how efficiently warmth travels from the permanent day side toward the darker hemisphere. As we continue our journey, every conclusion will rest upon the same careful ladder of evidence. Some discoveries are confirmed measurements, others are strong interpretations built from multiple observations. Beyond those lie plausible models that satisfy existing data, followed by unresolved possibilities awaiting future investigation. Keeping those distinctions clear allows us to appreciate both what has truly been measured and what remains hidden, beginning with the remarkable planet whose atmospheric chemistry inspired one of astronomy's most discussed ocean world interpretations. Among the growing catalog of distant planets, one world has drawn unusual attention from astronomers attempting to understand hidden oceans. Known as K218b, it circles a cool red dwarf approximately 120 light years from Earth. Each journey around its faint star lasts only 32.9 days, placing the planet within the region where incoming starlight could allow liquid water under suitable conditions. Careful measurements reveal a body unlike any planet in our own solar system. Its radius is about 2.37 times that of Earth, while its mass reaches roughly 8.9 Earth masses. Those values place it within a planetary family called subneptunes, meaning worlds larger than Earth yet smaller than Neptune. Although this category appears to be common throughout the galaxy, our own planetary neighborhood contains no comparable example, leaving astronomers with few familiar landscapes for comparison. The James Webb Space Telescope added another layer to the story by detecting methane and carbon dioxide within the planet's atmosphere. Researchers also reported an apparent shortage of ammonia, an observation that attracted considerable interest because some atmospheric models suggest ammonia could become depleted if a vast body of liquid water exists beneath a thick hydrogen atmosphere. That possibility inspired renewed discussion of a Hycean world, a proposed class of planet where a hydrogen rich atmosphere rests above a liquid water ocean. Hydrogen behaves differently from the gases surrounding Earth. It is remarkably efficient at trapping heat, allowing warmth to persist even when a planet receives relatively modest energy from its star. Because of that insulating effect, scientists have explored whether worlds beyond Earth's size might still maintain liquid water beneath extensive atmospheric layers. Yet you may notice that such an arrangement would differ profoundly from any familiar shoreline or open sea. Location alone offers no guarantee. A planet can orbit within a traditional habitable zone while still proving inhospitable near its surface. Atmospheric thickness, internal heat, pressure, and chemistry all influence whether liquid water can actually exist in a stable form. For K218b, those ingredients remain only partially known. An equally important point often disappears beneath dramatic headlines. The James Webb Space Telescope did not directly observe an ocean. It measured atmospheric molecules and their spectral signatures. Then scientists compared those observations with computer models describing possible planetary interiors. Several different combinations of atmosphere, temperature, pressure, and composition can reproduce portions of the same measurements with reasonable success. That leaves us balancing between evidence and interpretation. K218b may indeed possess an enormous ocean concealed beneath hydrogen. Another equally plausible picture places its deeper layers under temperatures or pressures so extreme that any Earth like sea becomes impossible. Both ideas remain consistent with significant portions of the available observations, reminding us that distant planets often reveal themselves gradually, one careful measurement at a time. From there, our attention naturally shifts beneath that immense atmosphere, where the boundary between gas and water may bear little resemblance to any ocean you have ever imagined. Imagine descending instead of sailing. On K218b, the greatest change may come beneath your feet rather than across the horizon. As we move downward through the planet's immense hydrogen atmosphere, every mile adds the weight of countless layers above, steadily increasing pressure until familiar ideas about sky, sea, and weather begin to lose their meaning. Atmospheric pressure rises because every layer of gas supports the layers above it. Earth experiences this effect as well, yet our atmosphere is comparatively shallow. A sub-Neptune, such as K218b, may possess a hydrogen envelope extending across extraordinary vertical distances. Hydrogen remains gaseous under conditions that would seem astonishing by terrestrial standards, allowing the atmosphere to continue far below any level we might casually describe as a surface. That creates an unexpected possibility. There may be no sharp boundary where open air suddenly becomes ocean. Instead, the atmosphere could gradually grow denser until gases and liquids merge through a broad transitional region. If such a water layer exists, it may begin without waves, breaking against a recognizable shoreline or a familiar sea level, marking the division between sky and ocean. Conditions become even stranger farther down. Some models allow hot liquid water beneath the hydrogen blanket. Others predict supercritical water. A supercritical fluid is matter compressed and heated beyond the point where liquid and gas can no longer be distinguished as separate states. Under those conditions, water no longer behaves like an ordinary ocean. It flows with unusual properties, lacking the clear surface that defines lakes and seas on Earth. Additional possibilities remain under active investigation. Water could contain large amounts of dissolved gases mixed throughout its upper layers. Increasing pressure may eventually force water molecules into dense crystalline structures known as high-pressure ice phases. Unlike the floating ice familiar on Earth, these exotic forms become stable only under crushing pressures deep within a planet, where temperatures may still remain remarkably high. Heat and pressure together also reshape chemistry. Molecules collide more frequently, reactions proceed differently, and materials that remain separate on Earth may dissolve or combine in unfamiliar ways. Such environments could become chemically aggressive, altering minerals and dissolved compounds long before they approach any rocky interior. One consequence has attracted particular attention among planetary scientists. A thick layer of high-pressure ice could separate the overlying water from the planet's rocky mantle. If that barrier exists, the ocean would lose direct contact with the rocks beneath, reducing opportunities for minerals and other ingredients to circulate upward through the water. This distinction matters because the presence of water alone does not automatically create an environment resembling Earth's oceans. Temperature, pressure, chemistry, and interactions with the planet's interior all shape whether a world can sustain conditions favorable for familiar biological processes. K. 2:18. B reminds us that an ocean can exist in forms unlike anything found at home. But another remarkable planet may offer evidence for abundant water through a very different line of investigation, beginning with its overall density rather than its atmosphere. Far from the unusual atmosphere surrounding K218b, another planetary system tells its story through timing. In the constellation Lyra, a cool red dwarf hosts several known planets whose repeated passages across their star have revealed subtle gravitational interactions. Each orbit slightly influences the others, causing tiny changes in the moments when their transits begin. By measuring those variations over many years, astronomers refined the planet's masses with remarkable precision. Among them, Kepler 138d stands apart. Observations show that it is substantially larger than Earth, yet its average density is too low for a world composed primarily of the same proportions of rock and metal found beneath our own feet. The measurements instead point toward a significant volume filled with material lighter than stone, while remaining much denser than hydrogen or helium. Water quickly became one of the leading explanations. It is abundant throughout planetary systems and possesses exactly the kind of intermediate density capable of helping reproduce the observed measurements. Even so, researchers are not imagining a larger version of Earth with familiar blue oceans stretching beneath open skies. The interior of Kepler 138d is expected to follow far stranger physical rules. As pressure increases with depth, water transforms into unfamiliar states. Large regions may exist as high-pressure fluid compressed far beyond ordinary terrestrial conditions. Other layers could consist of steam if the upper atmosphere receives enough energy from the nearby star. Still deeper, temperatures and pressures may create supercritical water where liquid and gas become indistinguishable. Beneath those layers, dense forms of high-pressure ice may develop despite the intense heat formed by compression rather than freezing weather. The atmosphere itself could also evolve in unexpected ways. If stellar heating proves sufficiently strong, large amounts of water may remain suspended as steam instead of condensing into liquid. That steam would influence surface temperatures, atmospheric circulation, and the balance between different phases of water, making the planet even less comparable to Earth's familiar environment. One remarkable implication comes from the planet's overall composition. If only several percent of Kepler 138d's total mass consists of water, that amount would already exceed Earth's entire ocean inventory by an extraordinary margin. On our planet, all the oceans combined account for only a tiny fraction of Earth's total mass. Here, water may represent one of the defining building blocks of the planet itself, rather than a comparatively thin surface feature. The neighboring planet, Kepler 138c, presents another intriguing possibility. Although it differs in several important characteristics, analyses suggest that it, too, may contain an unusually large quantity of water. Together, these neighboring worlds hint that water-rich planets may not be isolated curiosities, but one outcome of planetary formation under the right conditions. But composition inferred from density can lead us even further. Another super-Earth has measurements that permit an even larger reservoir of water, suggesting oceans whose depth could exceed anything our own planet has ever possessed. Some worlds reveal their character through chemistry, while others first announce themselves through weight. TOI 1452b belongs to the second group. This super-Earth circles one member of a small binary star system, where two stars remain gravitationally bound, even though the planet orbits only one of them. From our distant viewpoint, that arrangement adds another layer of complexity to an already remarkable world. Astronomers first identified the planet through repeated transits recorded by the Transiting Exoplanet Survey satellite, operated by the National Aeronautics and Space Administration. Follow-up observations refined the measurements, allowing researchers to determine both the planet's radius and its mass with much greater confidence. Those two values, considered together, provide the average density that has made TOI 11452b, one of the strongest candidates for a water-rich interior. Its density appears lower than would be expected for a planet built almost entirely from Earth-like proportions of rock and metal. One published interpretation suggests that water could account for roughly one-fifth to one-quarter of the planet's total mass. That figure comes from interior models rather than direct observation, yet it remains consistent with the available measurements and has drawn considerable scientific interest. For comparison, Earth's water inventory represents only a tiny fraction of our planet's total mass. Oceans dominate the appearance of Earth when viewed from space, yet they form only a remarkably thin outer layer compared with the rocky body beneath. On TOI 1452b, if the published models prove accurate, water would become a major structural component of the planet itself, rather than a comparatively delicate surface covering. That possibility also changes what lies below the uppermost layers. You might imagine diving through an ocean until reaching a familiar rocky seafloor, but such a journey may never end that way. Scientists instead envision a sequence beginning with the atmosphere, followed by an immense layer of liquid water or supercritical water, depending upon local temperature and pressure. Beneath that, high-pressure ice could form an extensive shell before the rocky mantle finally appears much deeper inside. An ocean extending hundreds of miles downward would create pressures vastly beyond anything found in Earth's natural environments. Under those conditions, water behaves according to unfamiliar physical rules, and ordinary expectations about waves, coastlines, and seabeds no longer provide reliable guidance. The deeper layers would exist within a realm where compression becomes one of the dominant forces shaping the planet's interior. Many uncertainties remain. The James Webb Space Telescope would need to study the planet's atmosphere in greater detail before researchers could better distinguish among competing interpretations. Even the measured density does not tell a complete story because a thick atmosphere, unusual interior chemistry, or different proportions of planetary materials can also reduce average density without requiring such enormous quantities of water. But TOI 1452b is only one expression of a possible ocean world. Another nearby super-Earth presents an entirely different vision, where liquid water may survive beneath a single region of everlasting daylight while the rest of the planet remains locked beneath ice. Instead of searching beneath an immense atmosphere, let us picture a world where geography may be shaped by permanent daylight. LHS 1140b is a temperate super-Earth orbiting a nearby red dwarf, and its measured size places it at roughly 1.7 times Earth's radius. Unlike several larger ocean world candidates, this planet occupies a range where a rocky surface remains entirely plausible. Its measured mass and radius allow more than one interpretation. Earlier studies could accommodate a substantial hydrogen envelope surrounding the planet, while other models suggested an interior containing a significant amount of water. As new observations accumulated, the balance of evidence gradually shifted. Measurements from the James Webb Space Telescope now make a thick Neptune-like hydrogen atmosphere appear less likely, increasing interest in the possibility that LHS 1140b could instead be a water-rich world. Even so, that interpretation remains promising rather than confirmed. The planet's orbit introduces another remarkable possibility. Many astronomers think LHS 1140b may be tidally locked. Tidal locking means a planet rotates at exactly the same pace that it circles its star, leaving one hemisphere facing the starlight continuously, while the opposite hemisphere remains in permanent darkness. If you stood beneath the star, it might never rise or set. It would simply remain fixed in the same place overhead. Climate simulations suggest that such an arrangement could produce a frozen world across much of its surface. Vast regions may remain covered beneath enduring ice. Yet the constant warmth beneath the overhead star creates an intriguing exception. Some models predict a circular body of liquid water centered on the point receiving uninterrupted daylight, surrounded in every direction by a global shell of ice. Researchers sometimes describe this feature as a bull's eye ocean. In several climate simulations, the liquid region reaches approximately 2,500 miles across. Near its center, modeled surface temperatures may approach about 68 degrees Fahrenheit, warm enough for liquid water under favorable atmospheric conditions. These values come from climate models built upon the planet's measured properties rather than direct measurements of the surface itself. Within those simulations, the warm central region becomes the engine driving the planet's weather. Water evaporating from the exposed ocean could form clouds directly beneath the stationary star. Those clouds might reflect part of the incoming starlight while releasing precipitation back into the liquid center. Winds would then carry air outward toward colder regions where temperatures fall and ice once again dominates the landscape. This remarkable picture remains an interpretation supported by current evidence rather than a confirmed description of the planet itself. Even so, it demonstrates how a world need not resemble Earth to maintain localized liquid water. The possibility invites us to reconsider familiar ideas about oceans, seasons, and coastlines. Here, an entire sea may owe its existence to a star that never appears to move, raising an entirely new question about how water circulates when daylight and darkness remain fixed forever. The pattern we have just explored may be more common than it first appears. Many planets discovered around red dwarf stars orbit remarkably close to their suns because those smaller stars produce much less light than our own. At such close distances, gravity gradually slows a planet's rotation until tidal locking occurs, meaning its spin becomes synchronized with its orbit. One hemisphere always faces the star, while the other always faces away. The point directly beneath the star is called the substellar point. There, the sun remains fixed overhead throughout the entire year. No sunrise begins the morning, and no sunset marks the evening. Far across the opposite hemisphere, the night side never receives direct starlight at all. Between those extremes lies a permanent boundary where daylight and darkness meet without ever advancing across the landscape. At first glance, such a planet might seem destined to become blistering on one side and frozen on the other. Yet, planets possess ways of redistributing energy. A sufficiently thick atmosphere can carry warmth away from the illuminated hemisphere through powerful winds. If liquid water exists, the ocean itself becomes another conveyor, moving heat across enormous distances beneath the surface. Climate models therefore produce several different possibilities instead of one universal outcome. Some simulations create only a modest opening of liquid water beneath the overhead star, surrounded by extensive ice. Others allow a much broader dayside sea, extending across a large portion of the illuminated hemisphere. Certain conditions produce a relatively narrow, habitable ring near the boundary separating daylight from darkness. In more extreme cases, a thin atmosphere may lose so much heat on the night side that atmospheric gases freeze onto the surface, a process called atmospheric collapse, because much of the atmosphere effectively disappears from circulation. Within any surviving ocean, currents would likely differ greatly from those on Earth. Persistent winds always blow within the same general circulation pattern because the heating never shifts across the globe. Constant energy arriving from one direction establishes enduring temperature contrasts. Differences in salinity caused by freezing ice or melting water could drive additional circulation, while dense cold water might sink beneath warmer surface layers before slowly returning toward the illuminated hemisphere. Earth experiences a continually moving pattern of daylight as our planet rotates. Every location takes turns receiving the strongest sunlight, helping distribute energy across the globe. A tidally locked world never changes that arrangement. The same region absorbs the greatest amount of stellar energy day after day, while the same hemisphere remains beyond direct illumination. Clouds may become an important balancing influence. Above the permanently heated substellar point, rising warm air could generate extensive cloud cover. Those bright clouds would reflect part of the incoming starlight back into space, reducing surface heating and helping stabilize the climate beneath them. For that reason, tidal locking alone does not automatically prevent habitability. The final outcome depends upon atmospheric thickness, ocean circulation, cloud formation, and the planet's overall composition. But these unusual climates become even more intriguing when we examine another compact red dwarf system, where several neighboring planets may once have possessed abundant water before their long histories took dramatically different paths. Rather than examining a single world, we now arrive at an entire planetary family. Around 40 light years from Earth, the TRAPPIST-1 system gathers 7 known planets that are all remarkably similar in size to our own world. Together, they form one of the most closely studied collections of rocky planets ever discovered beyond our solar system, offering astronomers the rare opportunity to compare neighboring worlds shaped by the same star. Every one of these planets travels closer to its parent star than Mercury orbits the Sunday. That might sound overwhelmingly hot, yet appearances can mislead. TRAPPIST-1 is much smaller, cooler, and dimmer than our Sun, allowing several of its planets to receive amounts of stellar energy comparable to those experienced by Earth. Because of that balance, multiple members of the system lie near or within the traditional habitable zone, where temperatures could permit liquid water under suitable atmospheric conditions. The planets also assist astronomers in another remarkable way. As they repeatedly pass in front of their star, their mutual gravity causes slight variations in the timing of those transits. These transit timing variations reveal how strongly the planets pull on one another, allowing researchers to estimate their masses with increasing precision. When those masses are combined with measured planetary radii, scientists calculate average densities that place meaningful limits on how much rock, iron, water, and atmosphere each world may contain. Those measurements leave room for intriguing possibilities. Some interior models permit substantial inventories of water on several planets within the system. Even so, no surface ocean has been confirmed on any member of the family. Density alone cannot distinguish between every possible combination of planetary materials, and several different internal structures remain compatible with the available observations. Recent observations from the James Webb Space Telescope have added another important piece to the puzzle. For some of the inner planets, the evidence increasingly argues against thick Neptune-like atmospheres rich in hydrogen. That finding narrows the range of possibilities, yet it does not immediately reveal whether thinner atmospheres or hidden reservoirs of water remain present. Studying these worlds also presents unusual challenges. The parent star is active, producing star spots, bright active regions, and energetic flares that alter the starlight reaching our instruments. Those changing stellar features can imitate or conceal atmospheric signals, making it more difficult to determine which spectral patterns belong to the planets themselves and which originate from the star they orbit. Viewed together, the 7 planets become a natural laboratory for planetary evolution. Their shared origin allows astronomers to compare worlds that formed from similar material while occupying different distances from the same red dwarf. The innermost planets endure the greatest stellar heating, whereas the outer members experience progressively cooler conditions. That orderly arrangement provides valuable clues about how neighboring planets can follow dramatically different evolutionary paths, leading naturally toward an even deeper question. How much water did these worlds begin with before the restless youth of their small star began reshaping their futures? The present appearance of the TRAPPIST-1 system tells only part of its story. To understand what these planets may have become, we must first consider what their star was like long before the planets settled into their current conditions. Young red dwarfs can remain unusually bright and highly active for extended periods, releasing far more energy than they do later in life. A planet resting comfortably within today's habitable zone may once have endured a far harsher environment. During that early era, several of the planets could have received enough radiation to trigger a runaway greenhouse effect. In such a process, surface water evaporates into the atmosphere. Water vapor then traps additional heat, causing temperatures to rise even further. As the planet grows hotter, still more water enters the atmosphere, strengthening the warming in a self-reinforcing cycle that becomes increasingly difficult to halt. The upper atmosphere then faces another threat. Energetic ultraviolet radiation from the young star can split water molecules into hydrogen and oxygen. Hydrogen, being extremely light, escapes into space far more easily than heavier gases. Once enough hydrogen is lost, the original water can no longer be reassembled. Oxygen may remain behind for a time, react with rocks at the surface, become incorporated into minerals, or gradually escape through other atmospheric processes. Several scientific studies suggest that some members of the TRAPPIST-1 family may have lost enormous amounts of water through these combined effects. Depending on the assumptions used, the losses could equal several times the amount of water contained within Earth's modern oceans. Those estimates illustrate the scale of the process rather than providing a final historical record. Important uncertainties remain. No one knows exactly how much water each planet possessed when it first formed. Their atmospheric compositions during youth also remain uncertain, and both factors strongly influence how much water survived. A planet beginning with an exceptionally abundant water inventory might lose several Earth oceans while still retaining vast hidden reservoirs beneath its atmosphere or within its interior. Distance from the star also changes the outcome. The innermost planets likely experienced the greatest exposure to intense radiation, making substantial water loss more probable. Farther outward, conditions may have been less destructive, allowing some worlds to preserve a larger fraction of their original inventories, despite enduring the same active stellar youth. Even if one of these planets appears dry today, its atmosphere or surface chemistry may still preserve clues pointing toward vanished oceans. Minerals altered by ancient water, unusual atmospheric compositions, or the absence of expected gases can all become pieces of a much older planetary history. In that sense, an ocean does not need to survive to leave evidence that it once existed. These possibilities remind us that planetary history can matter as much as present conditions. Two neighboring worlds exposed to the same star may arrive at dramatically different destinations, depending upon how much water they inherited from the beginning. That naturally leads us toward an even broader question, one reaching back to the birth of planetary systems themselves. Where do ocean worlds acquire such extraordinary quantities of water in the first place? Long before oceans spread across a planetary surface, everything begins inside a vast rotating disk surrounding a young star. Gas, dust, fragments of rock, and countless grains of ice circle together, slowly gathering into larger bodies through repeated collisions. Within this restless environment, the ingredients of future worlds are already being sorted according to distance from the newborn star. One boundary plays an especially important role. Astronomers call it the snow line, meaning the distance from a young star beyond which water can readily freeze into ice. Inside that boundary, temperatures remain high enough to keep most water in vapor form. Beyond it, frozen water becomes abundant, coating countless small objects and greatly increasing the amount of solid material available for growing planets. Planetary embryos, the early building blocks of full-sized planets, develop rapidly within these icy regions. As they collect surrounding debris, they accumulate not only rock and metal, but also enormous quantities of frozen water. Some eventually become rich in ice from their very beginnings, carrying far larger water inventories than planets assembled closer to their stars. Yet those young worlds do not always remain where they formed. Planetary migration describes the gradual movement of a planet through the surrounding disk as it exchanges momentum with gas and other material. Depending upon those interactions, an orbit may shift inward or outward over time. A planet born beyond the snow line can slowly migrate into a much warmer region while preserving much of the water gathered during its early growth. Water also arrives through many smaller travelers. Icy planetesimals, meaning small primordial bodies left over from planetary formation, repeatedly collide with growing worlds. Asteroids and comets contribute additional frozen material, while collisions between large planetary embryos can redistribute water across an entire developing system. Every impact changes the balance. Some deliver fresh supplies, while especially violent collisions can eject part of a planet's existing water back into space. Not every reservoir remains visible at the surface. Water can become locked inside minerals, where it is stored chemically within crystal structures deep below the crust. As the planet evolves, volcanic activity gradually releases part of that hidden inventory. Rising magma carries dissolved water toward the surface, where volcanic outgassing injects steam into the atmosphere. Over immense spans of time, this process may contribute significantly to a planet's atmospheric water content. Because so many pathways operate simultaneously, neighboring planets exposed to similar amounts of stellar energy may finish their formation with dramatically different quantities of water. One world may retain only scattered traces after repeated impacts and atmospheric loss. Another may preserve immense internal reservoirs inherited from icy regions far beyond its present orbit. Their temperatures alone reveal very little about those earlier histories. The story of an ocean, therefore, begins long before the first drop of liquid water appears. It starts with where a planet forms, how it travels, what strikes it, and how its interior continues releasing water across millions of years. Eventually, as internal heat slowly escapes and the atmosphere cools, a remarkable threshold arrives when endless steam finally begins changing into falling rain. Picture a newly formed rocky planet before its first ocean has ever existed. Its surface still glows from repeated giant impacts, while rivers of molten rock stretch across vast regions. Above that incandescent landscape hangs an immense atmosphere of steam mixed with carbon dioxide and other gases released from the planet's interior. Nothing resembling a familiar coastline has yet appeared. As molten rock slowly cools, dissolved gases escape through countless volcanic eruptions. Water stored deep within the young planet rises toward the surface as water vapor, joining the already dense atmosphere overhead. Carbon dioxide, nitrogen bearing gases, and many other compounds accompany it, creating an envelope far thicker than the atmosphere surrounding Earth today. Time gradually changes the balance. Every hour, every year, and every million years, the planet radiates heat into space. The upper atmosphere cools first, followed by lower layers. As temperatures continue falling, water vapor begins reaching conditions where it can condense. Condensation simply means water molecules gather together into tiny liquid droplets instead of remaining suspended as gas. Clouds begin to spread. Those droplets grow larger until gravity overcomes the upward motion of the atmosphere. Rain finally starts falling toward the blazing surface. At first, the journey ends quickly. The ground remains so hot that much of the rain flashes back into vapor almost immediately after landing. The atmosphere gains moisture once again, and another generation of clouds forms overhead. The cycle repeats relentlessly. Clouds gather, rain falls, water evaporates, steam rises. With every repetition, however, the surface loses a little more heat. Eventually, some rainfall survives long enough to collect in shallow depressions before evaporating again. As cooling continues across immense spans of time, those temporary pools become increasingly stable. On a planet that formed with abundant water, these repeated storms could continue for thousands of years, gradually filling low regions until a global ocean begins covering much of the surface. The transition would not necessarily happen all at once. Expanding seas would reflect more sunlight, influence atmospheric circulation, and slowly reshape the climate as the young world matured. Not every planet reaches that stage. A hotter world, receiving too much energy from its star, may remain trapped beneath a permanent blanket of steam. Atmospheric pressure also plays an important role because increasing pressure changes the temperature at which water boils. Under sufficiently high pressure, liquid water can remain stable at temperatures that would produce vigorous boiling on Earth. Another threshold is even more remarkable. Above roughly 705 degrees Fahrenheit, water reaches its critical temperature. Beyond that point, liquid water and water vapor lose their familiar distinction, merging into a supercritical fluid with properties unlike either ordinary gas or ordinary liquid. As a planet continues cooling below those extreme conditions, supercritical water can transform into true liquid oceans for the first time. Yet even after those oceans finally appear, the deeper layers continue evolving beneath immense pressure, where water begins following physical rules far removed from anything experienced within Earth's familiar seas. On Earth, the deeper you descend beneath the ocean, the colder the water generally becomes before reaching the seafloor. On a massive water world, the journey could end in something far less familiar. Instead of meeting solid rock, you might eventually encounter ice, even though the water above remains warm and entirely liquid. The reason begins with the unusual behavior of ordinary ice. The ice floating across Earth's lakes and polar seas forms an open crystal structure that is less dense than liquid water. Because it is lighter, it rises to the surface. This familiar property has shaped Earth's climate and oceans for billions of years, yet water possesses many other crystalline arrangements that appear only under extraordinary pressure. These are known as high-pressure ice phases, meaning compact arrangements of water molecules produced when immense pressure forces them into tighter structures. Several of these forms become denser than liquid water itself. Rather than floating, They remain buried deep below the overlying ocean, where compression completely transforms the character of frozen water. A sufficiently deep planetary ocean naturally creates those conditions. Even if the upper layers remain relatively warm, the tremendous weight of countless miles of water steadily increases pressure with depth. Eventually, the pressure alone becomes great enough to stabilize dense forms of ice. Temperature still matters, but compression becomes the dominant influence governing which phase of water can exist. Scientists therefore envision many water worlds as layered structures. At the top lies the atmosphere. Beneath it stretches a global liquid ocean. Far below, the water gradually transitions into an extensive mantle of high-pressure ice before finally reaching the rocky interior. Instead of resting directly upon stone, the ocean may be separated from the planet's mantle by an enormous frozen barrier hidden far below the surface. This deep ice bears almost no resemblance to a frozen pond or drifting polar iceberg. It forms under pressures reaching millions of pounds per square inch, creating dense crystalline materials unlike anything found naturally at Earth's surface. Although composed of the same water molecules, its physical properties differ dramatically from the familiar ice surrounding us during winter. That hidden boundary carries important consequences. Earth's oceans constantly exchange minerals with the rocky crust through weathering, volcanic activity, and hydrothermal circulation. Those interactions deliver dissolved elements that influence seawater chemistry over immense spans of time. If a thick layer of high-pressure ice completely separates the ocean from the underlying rock, much of that direct exchange may become greatly reduced. The picture may not be entirely static. Some planetary models suggest that convection could occur within the high-pressure ice itself. Convection is the slow circulation of material driven by differences in temperature and density. If such motion develops, portions of the icy mantle might gradually transport limited amounts of material between deeper layers and the ocean above, although far less efficiently than direct contact with exposed rock. But even that possibility leaves an important question. If a planet-sized ocean rarely touches its own rocky interior, many of the nutrients that shape Earth's seas could become scarce, changing the chemistry of an entire world hidden beneath seemingly endless water. Earth's oceans are never isolated from the world beneath them. Every wave, current, and tide belongs to a larger planetary system linking water, rock, and atmosphere through countless exchanges that continue every day. The chemistry supporting our seas depends upon that constant interaction, much of it occurring far beyond ordinary human sight. Rivers carry dissolved minerals from continents into the ocean after rain and erosion slowly wear down exposed rock. Volcanoes contribute fresh material from Earth's interior. Along the seafloor, hydrothermal vents release heated water enriched with dissolved elements, while ordinary seafloor weathering steadily alters oceanic crust through prolonged contact with seawater. Together, these processes replenish nutrients and maintain chemical cycles that have operated across immense spans of geological time. Now imagine removing nearly all exposed land. On a planet covered by an uninterrupted global ocean, continents may never rise above the water. Without broad areas of exposed rock, rainfall cannot produce the same extensive erosion that feeds Earth's oceans. Rivers, as we know them, would have no continents across which to flow. Several familiar pathways, delivering nutrients into seawater, could become greatly diminished or disappear altogether. The challenge grows even greater if a thick layer of high-pressure ice separates the ocean from the rocky mantle below. Instead of seawater touching silicate rock directly, An extensive frozen barrier may block much of that contact. Silicate rock, the dominant material making up Earth's crust and mantle, serves as an important source of many dissolved elements through long-term chemical reactions. Without regular access to those rocks, the composition of an ocean could gradually diverge from the conditions we recognize on Earth. One element receives particular attention in several scientific models. Phosphorus is essential for many biological processes familiar on Earth, yet it may become difficult to replenish efficiently within an ocean isolated from direct rock interaction. If only small amounts reach the water, phosphorus could become a limiting nutrient, meaning its scarcity restricts biological productivity, regardless of how much water is present. The immense size of these oceans also changes the behavior of carbon dioxide. Large quantities can dissolve into the water, potentially reducing the amount remaining in the atmosphere. On Earth, the long-term carbon silicate cycle helps regulate climate by moving carbon dioxide among the atmosphere, oceans, and rocks. A planet dominated by exceptionally deep water may weaken parts of that cycle if extensive ocean layers prevent efficient exchange with the underlying crust. Over billions of years, that difference could influence climate stability. A world containing enormous quantities of water may struggle to maintain the same self-regulating geological feedbacks operating on Earth. Yet these conclusions remain model-based possibilities rather than evidence that water worlds are incapable of supporting life. Other pathways may still provide essential materials: atmospheric dust settling onto the ocean, impacts from asteroids or comets, and gradual mixing from deeper planetary layers could continue supplying nutrients, even if less efficiently than Earth's interconnected systems. Those hidden exchanges occur within water that is rarely still. Across a planet-sized ocean, with no continents to interrupt its motion, entirely new patterns of circulation may emerge, carrying heat, dissolved materials, and energy around an uninterrupted world. A shoreline gives Earth's oceans a beginning and an end. Continents interrupt every major current, split vast bodies of water into separate basins, and steer heat along familiar paths. When we leave those boundaries behind, the geometry of an ocean changes completely. You and I are no longer looking at scattered seas, connected by narrow passages. We are looking at one continuous body of water, wrapping an entire planet. Without continents standing in the way, currents could travel extraordinary distances before meeting any obstacle. Water would still respond to gravity, planetary rotation, differences in temperature, and changing density, yet its routes would remain remarkably open. Energy absorbed beneath one region of the sky might continue flowing across much of the globe before gradually dispersing. One influence would remain impossible to escape. The Coriolis effect is the apparent deflection of moving air and water caused by a planet's rotation. Although the water attempts to move in a straight path, the rotating world beneath it causes that motion to curve. Every large-scale current and wind pattern must adjust to this constant turning. The speed of planetary rotation would shape the entire circulation system. A slowly rotating world could develop a small number of immense currents stretching across thousands of miles. Those broad flows might transport tremendous amounts of heat between distant regions. Faster rotation would produce a different arrangement. Instead of a few sweeping circulations, the ocean could separate into narrower bands, each following its own persistent course around the globe. Conditions become even more unusual on a tidally locked planet. Constant heating beneath the star warms the dayside ocean, while the opposite hemisphere steadily loses heat into space. Surface currents may carry warmer water away from the illuminated hemisphere toward the permanent night side. Far below, colder and denser water could sink before beginning a gradual return journey beneath the warmer surface layers, establishing a continuous planetary exchange. Ice introduces another source of motion. Whenever seawater freezes, much of the salt remains behind in the surrounding liquid, increasing its density. Where ice later melts, fresher water can spread across the surface. These differences in salinity, meaning the amount of dissolved salt, help drive additional currents that interact with temperature and rotation to produce remarkably complex circulation. Some models also suggest powerful equatorial jets racing around the middle of an uninterrupted ocean. Other currents may descend into great depths, moving so gradually that completing one circuit around the planet could require centuries or even longer. Despite their slow pace, these deep pathways steadily transport heat and dissolved materials across the world. Such circulation may prove surprisingly effective. By carrying warmth from the dayside into colder regions, a global ocean could reduce the likelihood that the entire nightside freezes solid, even beneath a motionless sky. Above those moving waters, another system begins to take shape, one where clouds, storms, and rainfall evolve without mountains or continents to interrupt their journey. From orbit, an uninterrupted ocean offers no familiar coastline where a storm must eventually lose its strength. On Earth, powerful hurricanes draw energy from warm seawater, yet they weaken rapidly after crossing land because their supply of heat and moisture is cut off. Mountains disrupt circulation, forests increase friction, and dry air begins replacing the moist air feeding the storm. Remove every continent, and that familiar interruption disappears. A planet covered almost entirely by water presents a very different stage. If atmospheric conditions are favorable, storms could continue traveling across vast stretches of warm ocean without encountering a single rocky barrier. That does not mean every ocean world must be wrapped in endless hurricanes. Storm formation still depends upon several ingredients working together, including suitable ocean temperatures, a supportive atmospheric structure, sufficient moisture, and planetary rotation capable of organizing the winds. As moist air rises, water vapor cools and condenses into droplets. During that process, latent heat, meaning heat released as water changes from vapor into liquid, flows into the surrounding atmosphere. That additional energy makes the rising air more buoyant, encouraging stronger upward motion. The cycle can reinforce itself as long as favorable conditions remain in place, allowing large storm systems to persist for remarkable periods. Atmospheric pressure also shapes the character of the weather. A denser atmosphere changes how air moves, how clouds develop, and how efficiently heat spreads through the lower sky. Winds may respond differently than they do on Earth, while cloud layers could extend through much greater depths before reaching colder altitudes where condensation slows. Even with familiar ingredients, the resulting weather may follow unfamiliar rules. The contrast becomes even greater beneath a hydrogen-rich atmosphere. Hydrogen weighs far less than the nitrogen dominating Earth's air, producing different pressure profiles, temperatures, and chemical behavior. Clouds might contain water in some regions, but higher layers could also include materials uncommon in our own atmosphere. The overall circulation would reflect a world whose sky shares little resemblance with the one above our oceans. On a sub-Neptune, the atmosphere itself may extend for hundreds of miles above the deeper layers below. Towering cloud decks could occupy only part of that immense vertical distance, while hazes suspended high overhead scatter and absorb incoming light. Those hazes matter because they can obscure what lies beneath, preventing telescopes from seeing whether liquid water exists below the cloud tops. If such a planet is tidally locked, weather may repeatedly organize around the hemisphere, receiving constant starlight. Persistent heating encourages rising air near the substellar region, while cooler air flows back from surrounding latitudes, establishing long lived circulation patterns that continually reshape the clouds. Far below that restless atmosphere, conditions may become surprisingly stable. The upper ocean absorbs the influence of winds and waves, yet deeper water changes far more gradually. As we descend farther still, another boundary begins to emerge, one where familiar oceans slowly give way to something far less recognizable, an atmosphere so dense that it begins to resemble an ocean itself. A planet does not need blue seas to earn a place among the most intriguing water worlds. Roughly 48 light years from Earth, GJ1214b circles, a small red dwarf, occupying a middle ground between familiar rocky planets and the larger ice giants. Its measured radius is about 2.7 times that of Earth, while its mass is approximately 8 times greater. Those values place it in a planetary category that our own solar system never developed. For years, astronomers attempted to study its atmosphere as the planet crossed in front of its star. Normally, different gases absorb specific colors of starlight, leaving recognizable patterns within the observed spectrum. GJ1214b repeatedly refused to reveal those fingerprints. Instead, the spectrum appeared remarkably flat, suggesting that thick clouds, or a dense haze, were blocking our view of the deeper atmosphere. The James Webb Space Telescope approached the mystery from another direction. Rather than relying only on starlight passing through the atmosphere, it measured subtle changes in the planet's infrared brightness as the world traveled around its orbit. Those observations allowed researchers to estimate how efficiently the atmosphere reflects, absorbs, and redistributes heat across the globe. The emerging picture points toward an atmosphere that is highly reflective and likely rich in heavier elements than a simple blanket of hydrogen and helium alone. Dense cloud layers, or persistent hazes, appear capable of hiding much of the lower atmosphere from direct observation. Even now, the full composition remains uncertain, yet the evidence favors a complex envelope rather than a clear sky. Temperature adds another important piece to the puzzle. GJ1214b is too hot to support an ordinary liquid water ocean exposed at the surface. Even so, water vapor may still represent an important ingredient within its atmosphere. Water has not disappeared from consideration. It has simply entered an environment where familiar oceans are no longer expected. Several interior models remain consistent with the available measurements. One possibility envisions a water-rich interior surrounding a rocky core beneath a massive atmosphere. Other models include mixtures of hydrogen, helium, water, and heavier molecules layered together under tremendous pressure. Current observations cannot fully distinguish among these possibilities, leaving several scientifically reasonable interpretations. This uncertainty reminds us that the phrase water world covers far more than one planetary design. Some worlds may possess deep liquid oceans beneath their atmospheres. Others may contain enormous quantities of water while exposing no accessible sea at all. Heat and pressure transform water into states unlike those found on Earth's surface, reshaping its behavior throughout the planet. When you picture an ocean, your imagination naturally reaches for rolling waves beneath an open sky. GJ1214b suggests another possibility, one where water exists inside an atmosphere so hot, dense, and chemically unfamiliar that the distinction between ocean and sky begins to blur. Beyond worlds like this, even water eventually gives way, replaced by landscapes where molten stone flows in place of every sea. Some worlds replace oceans of water with something even more extraordinary. Roughly 41 light years from Earth lies 55 Cancri e, also known as Janssen, a rocky super-Earth orbiting one of the stars in the 55 Cancri system. Its diameter measures almost twice that of our own planet, yet its orbit carries it astonishingly close to its star, at a distance of only about 1.4 million miles. That proximity changes everything. While Mercury circles far beyond such an extreme distance from the Sun, Janssen completes an entire orbit in less than 18 hours. The planet races around its star so rapidly that a full year there passes before a single day on Earth has nearly ended. Under relentless stellar radiation, much of the rocky surface is expected to remain molten. Current interpretations suggest that large regions, and perhaps nearly the entire surface, may consist of a global magma ocean. Magma is molten silicate rock, a complex mixture of melted minerals rather than one simple liquid. Instead of waves made from water, this ocean would consist of glowing stone flowing beneath an intensely heated sky. Temperatures likely climb into several thousand degrees Fahrenheit, keeping much of the outer crust from solidifying for extended periods. The heat becomes so intense that ordinary melting is no longer the only process shaping the landscape. Some rocks can begin to evaporate directly into the atmosphere. Atoms and molecules escape from the incandescent surface, creating a thin envelope composed of materials that would normally remain locked inside solid stone. On Earth, evaporation lifts water into the air. Here, the same physical principle acts upon minerals. Observations from the James Webb Space Telescope have strengthened the case for an atmosphere despite these severe conditions. Measurements are consistent with gases such as carbon dioxide, carbon monoxide, or other compounds released from the molten interior. The precise composition remains under investigation, yet the evidence points toward an atmosphere continually supplied by geological activity rather than one left unchanged over immense spans of time. Its persistence is one of the planet's greatest surprises. A world orbiting so close to its star experiences intense radiation capable of stripping atmospheric gases into space. Under those circumstances, you might expect the atmosphere to disappear entirely. Instead, the molten surface may continually replenish what is lost. Fresh gases escape from the magma, rise overhead, and replace material carried away by the harsh stellar environment, maintaining a dynamic balance between loss and renewal. The familiar water cycle has no place here. Rain, rivers, and oceans give way to a landscape governed by molten minerals, vaporized rock, and relentless heat. Instead of clouds forming from condensed water vapor, the atmosphere may contain substances released from glowing stone before eventually returning to the surface in altered forms. We have crossed into a planet where evaporation still drives change, but the cycle itself is built from rock rather than water. Imagine standing above a world where stone behaves the way water does on Earth. Under extreme stellar heating, solid minerals no longer remain locked within the crust. Elements such as sodium, along with molecules containing silicon and other rocky ingredients, can gain enough energy to escape from molten rock and enter the atmosphere. What rises overhead is no ordinary weather. It is an atmosphere supplied directly by an incandescent surface. The connection between ground and sky becomes immediate. Instead of oceans feeding evaporation, vast regions of molten rock continuously release mineral vapor. The atmosphere is not simply resting above the landscape, it is an extension of the landscape itself, carrying pieces of the planet upward before transporting them across the globe. Powerful winds may then move that vapor away from the hottest regions. As the gases drift toward cooler territory, especially near the boundary separating the permanent dayside from the darker hemisphere, temperatures decline enough for some mineral species to begin condensing. Condensation means that material suspended as vapor returns to tiny, solid, or liquid particles as it cools. The exact details remain under active investigation, yet planetary scientists have proposed that this process could produce a remarkable form of precipitation, often described as rock rain. No telescope has directly watched stones falling through such an alien sky. Instead, the idea emerges from physical models describing how vaporized minerals should behave under these extraordinary conditions. If those models are correct, condensed particles would gradually descend back toward the surface, completing a cycle unlike anything found on Earth. The sequence is elegant, despite its unfamiliar ingredients. Rock evaporates from intensely heated regions, mineral vapor travels through the atmosphere. Cooling allows some compounds to condense into particles. Those particles eventually fall back onto the planet, where extreme temperatures can melt them once again. The cycle begins anew, driven by heat rather than by the familiar exchange between liquid water and clouds. Not every substance participates equally. More volatile elements, meaning materials that vaporize more readily, can be transported through the atmosphere with greater efficiency than heavier or less easily evaporated compounds. Over immense spans of time, that difference may slowly redistribute chemical ingredients across the surface. Some regions could become enriched in particular minerals, while others gradually lose them through repeated atmospheric transport. Throughout this process, the atmosphere and the magma ocean remain tightly connected. Changes within the molten surface influence the gases overhead, while atmospheric transport determines where condensed material ultimately returns. Neither system evolves independently. Each continually reshapes the other through an ongoing exchange of heat, vapor, and minerals. But even this restless world may not represent the most dramatic expression of a lava planet. Farther along our journey, we encounter a place where the division between light and darkness grows even sharper, leaving one hemisphere glowing with molten rock, while the opposite side may remain locked beneath a frozen crust. K2141b belongs to an extraordinary class of planets known as ultra-short period super-Earths, worlds that circle their stars with astonishing speed. One complete year, there lasts less than one Earth day. Such an intimate orbit exposes the planet to relentless starlight, while powerful tidal forces steadily reshape its rotation. Over time, astronomers expect those forces to leave the planet tidally locked, meaning its rotation has become synchronized with its orbital motion so the same hemisphere always faces its star. That permanent orientation creates a landscape divided into two enduring realms. At the substellar point, the location directly beneath the star, the sun-like disk never drifts across the sky. It remains fixed overhead, pouring energy onto the same region without interruption. Computer models indicate that such persistent heating should maintain an immense ocean of molten rock across much of the dayside. Instead of waves made from water, this sea consists of glowing silicate magma, flowing beneath an atmosphere born from evaporation. The opposite hemisphere tells a very different story. There, the star never rises. Temperatures are expected to plunge far below those found on the illuminated side, allowing much of the surface rock to solidify. Between these extremes lies a gradual transition where conditions shift from blazing magma to hardened crust, creating one of the sharpest environmental contrasts known among rocky planets. Researchers have proposed that the molten region may reach hundreds of miles beneath the surface before giving way to deeper, solid layers. Above the hottest areas, the atmosphere should become thickest because intense heat continually vaporizes sodium and other rocky materials. Those gases rise directly from the magma ocean, forming a dynamic blanket whose composition depends upon the minerals below rather than upon oceans or forests. Planet-wide winds are then expected to carry that vapor toward cooler longitudes. As temperatures decline, sodium and other vaporized substances may condense into mineral particles before settling back onto the surface. This behavior remains a prediction based upon physical models, yet it follows naturally from the extreme temperature differences expected across a tidally locked lava world. The story does not end where those particles land. Beneath the crust, circulating molten rock may gradually transport material back toward the intensely heated hemisphere. Fresh magma reaching the surface can once again release gases into the atmosphere, linking the molten interior with the skies above through an ongoing exchange of energy and chemistry. Across immense spans of time, this circulation may slowly redistribute the planet's most volatile surface elements, while some material escapes into space altogether under relentless stellar radiation. K 2141b, therefore, offers more than a portrait of molten landscapes. It provides a natural laboratory where rock, atmosphere, and planetary evolution remain inseparably connected, preparing us to consider another lava world where the James Webb Space Telescope has revealed evidence for an atmosphere far thicker than many researchers once expected. Far from our own planetary neighborhood, we encounter TOI 561b, an ultra-hot rocky world circling its parent star with remarkable speed. One complete orbit lasts less than one Earth day. Such proximity exposes the planet to an extraordinary flood of radiation, making it one of the hottest rocky planets yet examined in detail. Instead of seeing only reflected starlight, the James Webb Space Telescope has measured the planet's own thermal emission, the infrared glow produced as its intensely heated surface releases energy back into space. Those observations revealed something unexpected. If TOI 561b possessed nothing more than bare rock beneath empty space, the permanently illuminated hemisphere should approach roughly 4,900 degrees Fahrenheit. Models based upon an airless surface also predict a dramatic contrast between the blazing dayside and the much colder hemisphere facing away from the star. Yet the measured distribution of heat does not fully match that simple picture. One explanation, receiving growing attention, is the presence of a substantial atmosphere capable of transporting energy across the planet. Rather than allowing the dayside alone to absorb nearly all the stellar heat, moving gases could carry part of that energy toward cooler regions. The result would soften the temperature contrast and produce the thermal pattern detected by the telescope. Although additional observations remain essential, this interpretation offers a compelling way to reconcile the measurements with physical models. Beneath that proposed atmosphere, researchers envision a broad global magma ocean. Magma is molten silicate rock containing many different minerals rather than a single uniform liquid. At such extraordinary temperatures, portions of the surface remain molten over immense regions, creating continual interaction between the glowing interior and the atmosphere above. Instead of oceans feeding clouds through evaporation, the molten crust itself supplies the surrounding gases. As minerals melt and circulate, dissolved volatile substances can escape from the liquid rock. Carbon dioxide, carbon monoxide, sulfur bearing compounds, and other gases may rise into the atmosphere through continuous outgassing. Scientists therefore suspect that this atmosphere is secondary, meaning it did not survive unchanged from the planet's original formation as a blanket of primordial hydrogen. Instead, it may be replenished again and again by the restless magma below. That ongoing exchange links the atmosphere directly to the planet's interior chemistry. Every gas released, transported, or lost carries information about the molten layers beneath the surface. By studying the infrared signatures of those gases, astronomers can infer properties of rocks they will never sample directly. In this way, observations made across dozens of light years become an indirect probe of an alien world's internal composition. You can almost picture the atmosphere and magma acting together as parts of one evolving system, each continually reshaping the other. TOI 561b reminds us that even the most hostile planets preserve valuable records of planetary evolution, leading naturally toward an even broader realization. The blazing magma oceans we observe today may resemble a stage that almost every rocky planet, including worlds far more familiar, experienced during its earliest history. Long before a rocky planet develops mountains, valleys, or familiar coastlines, its surface may exist as an immense ocean of molten stone. During planetary formation, countless collisions occur as growing worlds gather material from the surrounding disk. Some impacts are modest, while others involve bodies hundreds of miles across. The greatest collisions release enough energy to melt enormous portions of a planet, replacing solid ground with a glowing sea of magma stretching toward every horizon. This transformation rarely happens only once. As rocky planets continue to grow, repeated impacts can return them to molten conditions again and again. Beneath the surface, additional heat comes from the gradual decay of naturally radioactive elements trapped within the interior. Another powerful source appears as gravity pulls dense metallic material downward. Iron and other heavy elements sink toward the center, releasing gravitational energy that further heats the young world while helping to build its core. Our own planet almost certainly experienced these fiery stages. Geological models indicate that the early Earth possessed one or more global magma oceans before its surface became permanently solid. One especially dramatic event occurred when a Mars-sized body struck the young Earth, producing the collision that ultimately formed the Moon. The tremendous energy released during that impact likely melted a large fraction of the planet, creating another vast ocean of liquid rock before cooling could begin once more. These magma oceans were not shallow features. Depending upon the planet's size and the violence of its history, they could extend hundreds or even thousands of miles downward. Yet even such immense seas slowly evolved. As heat escaped into space, the molten material gradually cooled until the first crystals appeared. Those newly formed minerals did not all behave alike. Some were denser and tended to sink, while lighter minerals remained higher within the molten interior. Over immense spans of time, that separation helped establish the layered structure of the mantle that still shapes Earth's geology today. Cooling magma also released enormous quantities of gas. Water vapor escaped from the molten rock alongside carbon dioxide and nitrogen-bearing compounds. Rather than remaining permanently locked inside minerals, these volatile substances accumulated above the surface, forming one of the earliest atmospheres surrounding the young planet. That atmosphere continued changing as cooling progressed and the molten ocean slowly retreated. You can see how one ocean naturally prepared the way for another. A temporary sea of liquid rock supplied many of the gases needed for a future water cycle. As temperatures eventually declined far enough, water vapor condensed into clouds and rainfall, allowing liquid water to gather across the newly solid crust. In that sense, a water ocean may owe its existence to an earlier ocean of magma that shaped the planet from within. But not every rocky world receives the opportunity to complete that transformation. Around some stars, relentless stellar heating continually renews the molten surface, preventing those ancient magma oceans from ever giving way to permanent solid ground. Not every magma ocean belongs only to a planet's distant past. Some survive because the surrounding environment never allows them to cool. A planet continuously absorbs energy from its star while also radiating heat back into space. When those two processes remain in balance, surface conditions stay relatively stable. Yet for worlds orbiting extraordinarily close to their stars, incoming energy can remain so intense that molten landscapes endure instead of hardening into solid crust. Distance makes all the difference. Planets completing an orbit in only a few hours receive an uninterrupted flood of stellar radiation capable of maintaining melting temperatures across broad regions. Many of these worlds are also expected to become tidally locked, meaning their rotation matches their orbital period, and the same hemisphere always faces the star. That permanent day side receives relentless heating, while the opposite hemisphere loses energy into space under much darker skies. The molten interior contributes as well. As magma circulates beneath the surface, dissolved gases gradually escape into the atmosphere. Carbon dioxide, carbon monoxide, sulfur-bearing compounds, and other gases can accumulate above the planet. Some of these gases absorb outgoing heat before it escapes into space, strengthening the greenhouse effect and slowing the cooling of the molten surface. A sufficiently thick atmosphere, therefore, becomes more than a consequence of volcanic activity. It also helps preserve the conditions that allow volcanism and molten rock to continue. Gravity introduces another source of energy. On planets traveling along slightly elongated paths instead of perfectly circular orbits, changing gravitational forces repeatedly stretch and compress the interior. This process is known as tidal heating. The continual flexing generates internal friction, converting mechanical motion directly into heat. Even a modest amount of distortion, repeated without interruption, can supply a surprising amount of thermal energy over immense spans of time. Those orbital distortions do not always arise naturally. Neighboring planets can continually tug upon one another through gravity, preventing their orbits from becoming perfectly circular. As long as those interactions persist, tidal heating may continue beneath the surface. Instead of gradually freezing, parts of the mantle can remain molten because neighboring worlds never allow the interior to settle completely. Taken together, intense starlight, greenhouse warming, and tidal heating may keep some rocky planets partly molten for billions of years. Even so, these conditions are not necessarily permanent. Stars slowly change as they age, altering the amount of energy reaching nearby planets. At the same time, atmospheric gases may gradually escape into space through powerful stellar radiation or other processes. As that protective blanket becomes thinner, more of the underlying magma ocean may become directly exposed to space, changing the balance between heating and cooling once again. Beyond these blazing worlds, another class of ocean awaits our attention. Instead of glowing beneath relentless starlight, those hidden seas remain concealed beneath thick shells of ice, far from the warmth of any nearby sun. Imagine leaving every star behind. A rogue planet is a world traveling through interstellar space without orbiting any sun. Instead of tracing a familiar path around a parent star, it wanders the galaxy alone. Such planets are thought to form within ordinary planetary systems before powerful gravitational interactions eventually scatter them into the vast darkness between the stars. Those encounters can unfold when massive planets repeatedly disturb one another over millions of years. Each close pass slightly alters an orbit until one world receives enough energy to escape completely. Once ejected, the planet enters an environment unlike anything found within a conventional solar system. Starlight fades to little more than distant points, while the surrounding emptiness reaches temperatures only a few degrees above absolute zero. Yet darkness does not necessarily mean complete geological stillness. Some researchers have proposed that a sufficiently thick hydrogen atmosphere could act like an enormous insulating blanket. Hydrogen allows visible light to pass readily, but under the right conditions, it can also slow the escape of heat rising from the planet's interior. Instead of radiating freely into space, thermal energy becomes trapped beneath the atmosphere for extraordinarily long periods. That internal warmth has several possible sources. Radioactive elements buried within the rocky interior continue releasing heat as they gradually decay. Residual energy left over from the planet's original formation also escapes only slowly through the mantle. Together, these processes may provide enough warmth to sustain temperatures far above those expected from the surrounding interstellar environment. Some theoretical models therefore suggest that liquid water could survive beneath such an insulating atmosphere or below an extensive shell of surface ice. The ice itself plays an important role. Rather than merely covering the planet, it reduces the rate at which heat escapes into space. In that picture, the ocean receives warmth from below instead of sunlight from above, creating an environment fundamentally different from Earth's familiar seas. Even so, we should separate possibility from observation. No liquid ocean has been directly detected on any rogue planet. Current ideas arise from physical models describing how atmospheres, ice layers, and internal heat may interact under these extraordinary conditions. The concept remains scientifically plausible, yet direct confirmation still awaits future discoveries. Life on such a world, if it existed at all, would unfold without daylight or conventional seasons. Sunrise would never arrive because no nearby star would climb above the horizon. Any available energy would instead come from the planet itself. Geothermal chemistry could support reactions within the deep interior. Radioactive decay would continue supplying heat, while tidal heating might provide additional energy if the wandering planet retained a large moon whose gravity continually flexed the interior. These hidden worlds challenge our usual definition of a habitable environment. Instead of searching only for planets warmed by nearby stars, astronomers are increasingly developing instruments capable of distinguishing among these concealed possibilities, seeking subtle clues that reveal what may lie beneath darkness, ice, or a deeply insulating atmosphere. From across the immense distances between the stars, even the largest known exoplanets usually appear as far less than tiny dots. They cannot be spatially resolved into visible disks beside their host stars. Instead, nearly everything we learn comes from a minute change in light, sometimes no more than a single blended point, carrying clues from both star and planet. To understand those clues, astronomers examine a spectrum, meaning light separated into its individual wavelengths, much like sunlight spreading into a rainbow. Every gas absorbs particular wavelengths while allowing others to pass. These missing portions become distinctive patterns, often called molecular absorption features, simple fingerprints left behind as light travels through an atmosphere before reaching our telescopes. For worlds that may possess vast oceans, several molecules deserve careful attention. Water vapor is an obvious candidate. Carbon dioxide reveals important information about climate and atmospheric chemistry. Methane may point toward active geological or chemical processes. Carbon monoxide can indicate high temperature environments or atmospheric mixing. Ammonia becomes especially valuable in colder, hydrogen rich atmospheres. Yet finding any one of these molecules rarely proves that a liquid ocean exists beneath the clouds. The atmosphere itself shapes every observation. Temperature changes how molecules absorb light, while pressure broadens or narrows their spectral fingerprints. The same collection of gases may produce noticeably different patterns under different planetary conditions. You cannot simply match one pattern to a catalog and declare the mystery solved. Every spectrum reflects the combined influence of chemistry, heat, pressure, and atmospheric structure. Clouds complicate the picture even further. Thick cloud decks or widespread haze can hide deeper atmospheric layers, softening or nearly erasing many molecular signatures. Instead of displaying sharp features, the spectrum may become unexpectedly flat. This challenge has already appeared on several well-studied exoplanets, reminding us that an atmosphere can conceal as much information as it reveals. The host star introduces another complication. Dark star spots and brighter active regions alter the starlight passing through or around a transiting planet. If these stellar features are not carefully accounted for, they can imitate or distort atmospheric signals. Astronomers, therefore, compare repeated observations, searching for patterns that remain consistent instead of relying on a single transit. Additional techniques provide different pieces of the puzzle. Phase curves follow changes in planetary brightness throughout an orbit, allowing researchers to estimate how efficiently heat moves from one hemisphere to another. During a secondary eclipse, when the planet slips behind its star, astronomers briefly lose the planet's contribution to the combined light. Comparing the light before, during, and after that event helps isolate the planet's own thermal emission. Looking farther ahead, direct imaging aims to separate the faint glow of a planet from the overwhelming brilliance of its star. Future observatories may examine planetary light more independently than ever before. But every new capability also demands greater caution, because some of the most convincing signs of an ocean can emerge from entirely different processes, making careful interpretation just as important as sharper observations. Even after years of observation, the same measurements can support remarkably different planetary stories. We may calculate a planet's mass and radius with impressive precision, yet those values alone cannot reveal everything hidden beneath the atmosphere. Different combinations of rock, water, iron, and gas can produce nearly the same overall density. Astronomers call this the mass-radius degeneracy, meaning multiple internal structures remain consistent with the same observed measurements. An atmosphere adds another layer of complexity. A thick envelope of gas extends far above the solid surface, increasing the planet's apparent size during a transit. To our instruments, a rocky world wrapped in an expanded atmosphere can appear larger than its actual solid body. Without careful modeling, that extra radius could suggest a different composition than the planet truly possesses. Clouds complicate the picture further. Dense cloud layers or widespread haze can flatten a spectrum by hiding many of the molecular fingerprints below. Such a muted signal might resemble the atmosphere expected above a water-rich planet, even when another explanation proves equally plausible. The resemblance is intriguing, but resemblance alone does not establish the nature of the world beneath. Water vapor presents another important example. Detecting it within an atmosphere tells us that water exists in gaseous form. It does not automatically demonstrate the presence of a liquid ocean below the clouds. The atmosphere may simply be too hot for liquid water to survive anywhere on the surface. You can detect water while the planet itself remains entirely hostile to familiar seas. The habitable zone introduces another common misunderstanding. This region estimates how much stellar energy reaches a planet, assuming suitable atmospheric conditions. It does not guarantee temperate oceans. A world inside the habitable zone might possess a crushing hydrogen atmosphere, experience a runaway greenhouse that traps overwhelming heat, remain locked beneath global ice, or lose its atmosphere almost completely through stellar erosion. The host star also shapes every observation. Active regions, dark spots, and bright patches can alter the starlight passing through a planetary atmosphere during a transit. Those changing stellar features sometimes imitate atmospheric signatures or weaken genuine ones, making interpretation substantially more difficult than the measurements alone might suggest. Researchers therefore compare observations collected by different instruments and repeated over many transits. Tentative detections of molecules occasionally receive competing explanations as additional data arrive. Rather than forcing certainty where evidence remains incomplete, scientists usually publish a range of possible interpretations. That approach reflects the limits of present observations instead of any weakness in the scientific process. Uncertainty is part of discovery. Each unanswered question marks the boundary between what we presently know and what improved observations may eventually reveal. As more capable observatories continue examining distant planetary systems, the strongest ocean world candidates will gradually emerge from overlapping lines of evidence instead of any single remarkable measurement. A convincing discovery will almost certainly emerge through agreement rather than surprise. Instead of relying on one extraordinary observation, astronomers expect several independent lines of evidence to converge until competing explanations gradually become less likely. Only then can a distant world begin to resemble a genuine ocean planet instead of merely another intriguing possibility. The process starts with better measurements of planetary mass and radius. Together, these values limit the range of possible interiors, helping researchers distinguish between combinations of rock, iron, water, and atmospheric gas. Smaller uncertainties narrow the list of plausible worlds. They do not eliminate every alternative, but they steadily reduce the number of models that remain consistent with the observations. Atmospheric pressure provides another essential piece of the puzzle. Pressure determines whether liquid water can remain stable at the surface, or whether it must exist only as vapor or ice. Although measuring pressure directly across dozens of light years remains extremely difficult, subtle atmospheric signatures may eventually place meaningful limits on the conditions surrounding a planet. Chemistry also offers important clues. Scientists search for combinations of gases that naturally coexist with liquid water over long periods. No single molecule provides decisive proof. Instead, researchers examine how different gases interact under known physical laws, asking whether the atmosphere behaves as though it is exchanging material with a stable ocean below. Infrared phase curves add another perspective. By tracking how a planet's heat changes throughout its orbit, astronomers can build temperature maps across different longitudes. Efficient heat transport may suggest an atmosphere capable of redistributing energy, while unusual temperature contrasts reveal additional details about circulation, cloud formation, and possible surface conditions. Reflected light carries different information. It may reveal the extent of cloud coverage, the brightness of the surface beneath the atmosphere, and important characteristics of atmospheric composition. Among the most intriguing possibilities is ocean glint, the bright reflection produced when a smooth liquid surface catches starlight at a favorable angle. Yet even this promising signal requires caution. Clouds or extensive ice fields can create similar reflections, making careful interpretation essential before reaching any conclusion. Another promising technique studies polarization, the preferred orientation of light waves after reflection or scattering. Different surfaces and atmospheric particles alter polarization in distinctive ways. Liquid water, clouds, ice, and bare rock each influence reflected light differently, offering another opportunity to separate competing explanations when combined with other observations. Future large space telescopes designed to image Earth-sized planets around Sun-like stars may finally gather enough detailed light to apply all these methods together. Even then, astronomers will want observations collected across changing orbital phases and, whenever possible, different seasons. A true confirmation will probably resemble a carefully assembled mosaic rather than a single dramatic photograph, gradually revealing that somewhere beyond our own skies, an entire world may indeed be covered by water. After exploring so many unfamiliar worlds, it becomes natural to look back at our own with fresh perspective. Earth is often described as an ocean planet because water covers about 71% of its surface. From space, broad expanses of blue dominate the view. Yet beneath that familiar appearance lies a planetary arrangement that may occupy a surprisingly balanced position among the many possibilities nature can produce. Although the oceans are extensive, continents still rise above the waves across every hemisphere. Vast regions of exposed crust remain open to wind, rain, rivers, and changing seasons. Mountain ranges, volcanic landscapes, and broad plains continually reshape the boundary where land, water, and air meet. This combination differs greatly from theoretical worlds that may possess tens or even hundreds of times more surface water than Earth. Our oceans are also remarkably thin when compared with the size of the planet itself. Earth spans nearly 8,000 miles from one side to the other, while the average ocean depth measures only a small fraction of that distance. The seas appear immense to us, yet they form little more than a delicate outer layer resting upon a much larger rocky world. That geometry allows constant interaction among the ocean, atmosphere, continents, and rocky seafloor. Rivers carry dissolved minerals toward the sea. Ocean water reacts chemically with exposed rock. Volcanic activity introduces new material from below, while sediments gradually return elements to the crust. These exchanges connect Earth's major systems into one evolving planetary network. Plate tectonics plays an especially important role. As enormous sections of crust slowly move, collide, and sink back into the mantle, they recycle material over immense spans of time. Weathering, the gradual breakdown of exposed rock by water and the atmosphere, removes carbon dioxide from the air and stores it within minerals before geological processes eventually release part of it again. Together, these mechanisms help regulate climate across millions of years, even as the sun itself slowly changes. Planetary models suggest another possibility. Earth may occupy a narrow middle ground between relatively dry, rocky worlds and planets buried beneath extraordinarily deep global oceans. There appears to be enough water to support an interconnected biosphere, while still leaving continents and shallow ocean floors exposed to participate in long-term geological cycles. This does not demonstrate that such a balance is the only path toward life. It simply reminds us that other water-rich planets may operate through very different physical and chemical relationships. The word ocean, then, carries far more meaning than it first seems. On one planet, it may describe familiar coastlines and rolling tides. On another, it could refer to a sea resting above high-pressure ice, hidden beneath permanent darkness, or buried below an atmosphere unlike anything we know. As our catalog of distant worlds continues to grow, those many versions of an ocean steadily broaden our understanding of where habitable environments might begin and where their limits may ultimately lie. Across the galaxy, water is remarkably common. Astronomers detect its signature within interstellar clouds where new stars begin forming. It appears inside swirling protoplanetary disks, the vast rings of gas and dust that surround young suns. Comets preserve frozen reservoirs from the earliest stages of planetary formation. Many moons contain hidden stores beneath ice, while planetary atmospheres across distant systems often reveal traces of water vapor. As our observations expand, water itself seems less like a rarity and more like one of the universe's familiar ingredients. Yet abundant water does not automatically create an enduring surface ocean. Liquid seas require a delicate combination of physical conditions working together across immense spans of time. A planet needs temperatures that allow water to remain liquid, atmospheric pressure sufficient to prevent rapid boiling or freezing, an atmosphere stable enough to endure, and a long-term balance between incoming stellar energy and the heat escaping back into space. When too little atmosphere surrounds a rocky world, water may gradually freeze across the surface or drift away into space after sunlight breaks its molecules apart. The opposite extreme presents different challenges. An atmosphere that becomes excessively thick can trap enormous amounts of heat, producing crushing pressure and temperatures that prevent ordinary surface oceans from surviving despite the continued presence of water. Even an extraordinary abundance of water introduces another possibility. Some planetary models suggest oceans so deep that immense layers of high-pressure ice form between the liquid water and the rocky mantle below. If that barrier persists, the ocean becomes largely isolated from the minerals and chemical exchanges occurring within the interior. Such isolation could influence how nutrients circulate, although scientists continue exploring exactly how significant those effects might be. The parent star shapes this story as well. Powerful stellar flares can bombard nearby planets with energetic radiation and charged particles capable of stripping away portions of an atmosphere over time. A world that appears inviting today may have experienced billions of years of atmospheric erosion, while another planet farther away could have preserved a more stable environment throughout its history. That history matters every bit as much as the planet's present orbit. Two worlds receiving nearly identical amounts of starlight may arrive there through completely different evolutionary paths. One may retain oceans that have remained stable for immense ages. Another could have lost most of its atmosphere long before conditions became favorable again. We therefore cannot assume that every ocean planet offers a home for biology. Many may remain entirely sterile despite containing enormous quantities of water. Others may possess environments where chemistry unfolds in ways that could support living systems. At present, however, no observation has confirmed the existence of life on any exoplanet. As we continue refining our instruments, you and I find ourselves listening across light years, gathering faint signals from distant oceans that humanity may never physically reach. allowing patient observation to become the bridge between our world and theirs. Every ocean we have explored during this journey remains hidden from direct view. No spacecraft has crossed those distant waters. No camera has looked across their horizons. Every possibility begins with an astonishingly small collection of photons, tiny packets of light that have traveled for years, decades, or even centuries before reaching our telescopes. From those faint signals, astronomers attempt to reconstruct entire planetary environments. A complete world may appear only as subtle changes within a spectrum, the light separated into its individual wavelengths. Gravity reveals a planet's mass. Heat reveals how energy moves across its surface and atmosphere. Chemistry leaves delicate fingerprints within the light itself. Piece by piece, an unseen ocean becomes a scientific possibility rather than an imagined landscape. Those distant clues may describe endless water concealed beneath towering clouds. They may point toward a warm sea trapped beneath a shell of global ice. Another spectrum may hint at steam compressed beneath immense atmospheric pressure where familiar shorelines could never exist. Elsewhere, the same techniques may reveal an ocean of molten rock flowing beneath a glowing atmosphere, reminding us that the word ocean describes movement and scale as much as composition. Yet observation and experience remain separated by extraordinary distance. Even the nearest promising candidates lie many light years away. With present human technology, reaching them would require journeys extending far beyond any mission our civilization can undertake. For now, we explore with mathematics, careful measurements, and patient interpretation instead of footsteps. As you compare these worlds with our own, familiar language begins to stretch. On Earth, an ocean brings to mind waves breaking along beaches, rain falling from clouds, and a horizon where water meets the sky. Those experiences shape the meaning of the word from childhood onward. Beyond our solar system, an ocean may possess no exposed shore, no recognizable sky, and no clear boundary separating liquid from atmosphere. It may exist beneath ice, beneath steam, or beneath pressures that transform water into unfamiliar states. The answer, then, is broader than it first appears. These impossible oceans are not a single class of destination. They form a wide spectrum of scientifically plausible environments, inferred indirectly through gravity, heat, atmospheric chemistry, and the faint light collected across unimaginable distances. Each new observation narrows uncertainty without completely removing it. So we end where every discovery truly begins, beside the modest ocean of our own world. Humanity stands upon one small shoreline, lifting telescopes toward distant stars and searching for seas that may never be visited. The galaxy may contain far more oceans than earlier generations imagined, yet the first confirmed alien sea still waits beyond the limits of human sight, inviting us to continue listening to the light that crosses the darkness between worlds.